For this video, I'm going to give you an overview of the idea, and then I'm going to show you 3 example problems that illustrate the idea. Watch as much or as little of this video as you need for this concept to make sense to you. Empirical formulas are based on actual atom counts present in molecules. This means that we can only round a calculated molar value if we are very close to the next whole number, as our atoms are indivisible. When I say very close, I so very mean it. Values with decimal places greater than 0.9 can be rounded up, and those with values that have a 0 in the tenths place can be rounded down. Other than these instances, the decimal place values will likely represent a common fraction of an atom. What this actually indicates is that all of our molar values are a fraction of what they should be, and we need to multiply each value by the same multiple to get rid of that fraction before we can report our final empirical formula. Now, you'll be responsible for recognizing when you have values related to the half, to the thirds, and to the quarters. An easy way to eliminate fractions is to multiply them by their reciprocals. In the case of 1/2, we will end up multiplying all of the moles values in the problem by 2. 1/2 times 2 really is just 2 over 2, and that really is just 1. So this operation leaves us with all whole numbers. We'll have to multiply each value by 2, even if those that are already whole numbers, because these problems are large mathematical operations, and what we do to one part of them, we have to do to every part of them, because they are all part of the same chemical formula. Now, similarly, if you have values that are or can reasonably be rounded to 0.33 or 0.66, you have values in terms of thirds. Multiplying everybody by 3 will eliminate these values and are going to leave you with whole numbers. The least common option here are probably the quarters, but they do show up from time to time, so they're worth mentioning. Your calculated values here are going to be very close to 0.25 or 0.75, and if you multiply everything by 4, you'll end up with whole numbers. While it's possible that you can have 2 values in the same problem that represent the same family of fractions, you won't have values that represent 2 different families of fractions. For instance, I can end up with the 2.66 and 1.33, which are both a third and 2/3, but I won't end up with 2.66 and 1.25, which would be a third and a quarter. So you'll only ever have to multiply everything by a single whole number to eliminate your fractions. It's important to keep in mind that any question you see on a quiz, and the vast majority of questions that you see on homework or other practice, have been idealized so that they work in a Gen Chem setting. So values that you calculate should be very close to either rounding to the whole number or will be very close to rounding to one of these fractions. If your values are somewhere in between, then you've likely made an error somewhere and you want to double check your figures. I'm not going to work out these 3 problems, but I strongly encourage you to as extra practice. It's in your best interest to pause the video now and get through that step where you divide all of your calculated molar values by the smallest of them, as that's where I'm going to pick up. So go ahead and do that now. After making the assumption that there are 100 grams of sample, converting from mass to moles of each element, and dividing all of the moles values by the smallest among them in hopes of whole numbers, I am left with the following values here. Please note that I carried as many decimal places for as long as I could prior to this point. You will want to do the same, as not doing that might cause rounding errors and you might not get to this point. At any rate, I have 2 values that I cannot round to the next whole number. There are a few problems with just rounding at this point. First, atoms again are indivisible, so anything too far from a whole number is an indication that all of our values here are too small. This brings up a second problem though. Just ignoring the half of the atom would throw the ratio of all of the atoms included in the empirical formula off. And since an empirical formula is really just a whole number ratio of atoms within a compound, we'd be goofing the one thing that we are intending to find. So we're going to have an extra step here in this problem that we don't necessarily always have. The decimal value 1.5 is the same as both 1.5 or 3/2. If I know that I'm trying to move away from a fraction, and I know that there's a 2 in the denominator of that fraction, then multiplying 3/2 by 2 should do the trick. I've included my 2 as a 2 over 1 here in case that helps someone see the process better, but really it's just a plain old 2. Even though there are only 2 values here that are actually in terms of 1/2, we're solving for one single empirical formula, making all of these individual calculations part of one larger calculation. And that, in turn, means that what I do to one part of the calculation, I'll have to do to all of the other parts. So we're going to multiply all of our values here by 2. Doing so results in the ratios that we will eventually put in our empirical formula. Again, pause the video right now and get to the same point that I started from in the last example. This time, instead of numbers in terms of halves, after I divide all of the calculated moles values by the smallest among them, I'm left with 2 different fractions in terms of thirds. I have 1 1/3 moles of carbon and 2 2/3 moles of hydrogen here. Same song, different verse. The decimal value 1.33 is the same as 4/3. Since there's a 3 in the denominator here, multiplying 4/3 by 3 will ultimately leave me with a whole number. Very similar story is true for the 2.66 value associated with the hydrogen. Again, there may be problems that require you to reduce more than one fraction, just like this one. But also like this one, you'll reduce them all using the same multiple. Again, all of our little pieces here represent one larger calculation. So what you do to one part, you'll have to do all of the other parts, even if there isn't a fraction associated with those at the moment. Since you multiplied the values for carbon and hydrogen by 3, you'll also need to multiply the value for oxygen by 3 before you can determine that final mole ratio and before you can report the empirical formula. Again, pause the video and get to the same point that I started from in the first 2 examples. Here we see that we have 3/4 of a mole of hydrogen, and you won't see either 3/4 or 1/4 very often, but you really need to look out for them. You might be tempted to round these up or down as they aren't terribly far from a whole number. They are, however, far enough away that it really does matter. And this is a great time to warn again about not carrying enough decimal places through your calculation. If you skimp on that in this case, you might be even more tempted to round and be further off from your actual empirical formula ratio. 4.75 moles is the same as the semi-wonky fraction 19/4. If you multiply this fraction by 4, you'll just end up with 19. Remember to multiply all of the atoms in your equation by 4, and you'll have your ratios, and then you can report your empirical formula. Note that 1/4 was the smallest fraction we've seen, which resulted in the largest multiple and the biggest change to the moles values in our formula. So there are none of these fractions that we could ignore.